Now we are going to do the confidence interval for the population standard deviation. So, my formula. The formula looks like this. We are going to have the square root of n minus 1 times s squared over the chi squared sub alpha divided by 2 with how many ever degrees of freedom that we have to do, which is going to be n minus 1 for your degrees of freedom like we had before when we were doing the t's, right? So it says pilots who cannot maintain regular sleep hours due to their work schedule often suffer from insomnia. A recent study on a sleeping pattern of pilots focused on the quantifying deviations of regular sleep hours. A random sample of 29 commercial airline pilots, so we know N, going to be 29, was interviewed. And the pilots in the sample reported the time at which they went to sleep on their most recent working day. The study gave a sample mean and standard deviation of the times reported by pilots, with these times measured in hours after midnight. Thus, if the pilot reported going to sleep at 11 p.m., the measurement was minus 1. The sample mean was 0.8 hours, and the standard deviation was 1.8 hours. Notice in this formula, we don't even need to know the sample mean. We don't have an X bar in there, but we are going to do the standard deviation. The sample standard deviation was the 1.8 hours. We are going to have a 90% confidence interval. And so again, when we do that, we know 90% is in the middle. 1 minus 90% is our 10%. 10% divided by 2 is 5%. So that alpha divided by 2 number is going to be 0.05. Just like we did on all those other ones, right? Now, when we calculate this, are actually calculating from there to here. So when we do this one, we are not going to use 0.05. We're actually going to use 0.95. Because we're going to go all the way from here to here. So we have our 90% plus that 5% on the end. So it's a little bit different than those other ones were. My formula, I have the square root of n minus 1, so 29 minus 1. Then I'm going to have my s squared, so I'm going to have 1.8 squared over, we're going to use chi squared, and we're going to use the 0.95 with a degree of freedom of n minus 1. We had 29. 29 minus 1 is 28 then for our degrees of freedom. Now, if you wanted to right away, you could just do 29 minus 1 and use 28 when you type it into your calculator, or you could use the parentheses and put 29 minus 1 in there, either way. But that's what you're going to punch into your calculator.
How do I make this square?
The 1.8?
Yeah.
Right there where it has the x squared. Highlight it? Yep.
write it down, but
What did you get? You don't know? Okay, whoops, on the bottom,
oh
whoops.
shit.
Hit undo. Okay, highlight, okay, there you go. Now you want to use this one right here, chi squared. And you're going to use 0.95 with 28 for our degrees of freedom. Okay, and you hit equals, you get 2.31, right? You get 2.31? Okay, 2.31, that's actually your upper limit. Your lower limit, I don't know why I did these in reverse order, but it doesn't matter, is you're going to use the exact same formula, but now you're going to find this section here. So basically all we're going to do then is use our other value, which was our 0.05, right? That section there was 0.05. So you're going to use the same formula, just change your 0.95 to 0.05. So that one gives us the upper, this one will give us the lower.
So we have to type all that again?
You probably could undo a couple times and then just change your number maybe.
Yeah, that works.
Does that work?
Yeah, I got one thing.
So if you undo and then this cursor over and make that 0.05 instead of 0.95, you got what?
1.48.
1.48, yep.
So, and then just leave it 28?
Yep.
Freedom?
Yep, the 28's going to stay the same.
1.4?
Yep. So we're actually going to do this formula twice. One with the value that we got when we did alpha divided by 2, and one when we do our complement of that. Those two numbers should add up to the 100%. All right. Now the next one, again, they weren't so nice on. Instead of just giving us our data, they gave us the list. So this is what we're going to do the same thing we did before when we had a list. We're going to grab our graphing calculator, put our numbers, stat 1 to type our list in. Cursor up, clear out what's in there. And we just have 5 numbers this time. 1 and 57. Once we have our list entered in, we do stat calculate one variable statistics. So stat calc number 1 for one variable statistics on list 1. And so our formula, for our formula, we needed to know n. N is equal to, how many numbers did we have on our list? 5. We need to know our S of x. Our S of x is 6.164. We're doing our intermediate computations to 3 decimal places, so that would be good to use. And do we need anything else for our formula? We need to do our subs. So we're going to have a 90% confidence interval. So if this is 90%, is that what we had before?
Yeah.
Okay, then we know we're going to have 0.05. So we're actually going to use 0.95 and 0.05 for our 2 values, right? So in our formula, we had the square root of n minus 1, 5 minus 1 is 4, times our standard deviation squared, so 6.164 squared over chi squared. And one time we're going to do 0.95, the other time 0.05, doesn't matter which. Well, if you want to do the lower one first, it might make more sense. I don't know why I did it the other way around, but hey. Both of our 2 values and our degrees of freedom. What are we going to use for our degrees of freedom? 4, n minus 1. So the degrees of freedom is n minus 1, 5 minus 1 is 4. put those two things into our calculator on Alex. Just to remind you of how we did that. I should have had one of you do 0.95 and the other one do 0.05, and then we would have had both our answers. Didn't we?
0.05.
0.05 gave you what for your answer?
4.003.
4.00. We're just going to do it to 2 decimal places, so 4.00. And our upper limit
I don't know what I'm doing wrong.
maybe you did the upper one and she did the lower one. Oh, you didn't do your x chi-squared. Let's back this up. Get rid of all that. Back that up one more. All right, so we're using this right here, chi-squared. And then we're putting in 0.95 with 4 degrees of freedom. All right, so when you do that, you come up with
14.62.
Yep. 14.62 is what you should end up with. Exactly. So anytime when you're doing these problems, when they give you that list, you could calculate the mean and the standard deviation using the long formulas, but much easier just to put your list in your calculator and figure them out that way. Number 9, psychologist wants to estimate the standard deviation of IQ scores. It is widely believed that the IQ scores follow a normal distribution. Her random sample of 24 IQ scores has a mean of 104.5 and a standard deviation of 13.3. Find a 90% confidence interval for the population standard deviation based on the sample. All of these gave us 90%. If they'd stick with that, that'd be nice. So, if I'm going to stick those into my formula, what am I going to have? What do I know?
The N is 24.
N is 24. So, N minus 1 would be 23. That's also my degrees of freedom. Okay? Got to look back at the previous ones. What was in the formula next? What's your value for S?
Standard, no.
Yep, that's your
13.3.
13.3. That's your standard deviation, right? And so we have 13.3, if I could write the 3, squared, according to our formula, over chi-squared sub, and since we have 90% again, we know we're going to use 0.95 and 0.05. And my degrees of freedom, 23. So even though they give us the mean, we don't need to know the mean, we just need the standard deviation for this formula, which goes right there. So square root of 23 times 13.3 squared over go. I like that. 5, yep. And chi squared. Yep. And 9, 5 with a degree of freedom of 23. 17.63. So for our upper limit, 17.63, because that was the 0.951, right? That's going to give you your upper, your lower one, then you're going to do the 0.05. 10.76 and 0.76. All right.